So, welcome back. We're still continuing our topic of section 9.7, approximating functions with polynomials. Last time we saw how we approximated e to the x, how to approximate e to the x with a polynomial of nth degree near 0. More generally, if you want to approximate a function near a polynomial, with a polynomial near some other c, it's convenient to consider the polynomial Pn of x is a naught, the constant term, plus the linear term x minus c, plus the square term x minus c squared, plus all the way to the nth degree term x minus c to the power n. The idea of having x minus c's here is, think back about what does subtracting c, a constant, from every x do. Given a function, replace each x by x minus c, x minus 5, let's say, to be more concrete. What does that do? What does that do is, okay, x initially when x is 0, then when x minus 5, x equal to 5 makes that term 0. So essentially it shifts the graph. So once we learn how to do it very nicely for 0, the idea here is to, instead of working with more algebra where this is polynomial expression of just x's, we just shift the graph and then work it at any point we want to work it at. Okay, so now take this polynomial, right? We're going to do the same approach, do differentiation. We want the values of the first, second, third, and so on and so forth derivatives at c equal to our original function. So what are the derivatives of this polynomial? The first derivative would be the constant term will go away, and the linear term will become the constant a1. Right? The derivative inside is just 1. So then plus 2a2 x minus c plus 3a3 x minus c squared plus n x minus c to the power n minus 1. So it becomes a polynomial of degree n minus 1. As you know, a polynomial goes down in degree when you differentiate it. I'm not going to do all derivatives, of course, but let's just do a couple of these so that you get the general pattern of how these things look like. Let's look at the second derivative. Now this term will go away and you'll be left with 2a2 plus 3 times 2, this 2 will come down, a3 x minus c plus n times n minus 1 an x minus c to the power n minus 2. Right? I'll do one more and then write down the general one. Let's do the third derivative. And recall this notation. When you put a number in the power but with parentheses, it means that derivative. So right now I'm working on the third derivative. This will be, this constant will go away. This will be just 3 times 2 times, I'll make it 3 factorial. Right? 3 factorial a3. What do you think has happened to the fourth degree term earlier? The fourth degree term had become a 4, then an extra 3 came, and this time 2 will come, a4, and now it has become a linear term. Right? This was the term that started with power 4. 4 came down, then 3 came down here, then 2 came down, and it has reached this stage. Plus n times n minus 1 times n minus 2 an x minus 3 to the power n minus 3. Okay? So now I'm going to go ahead and write down the nth derivative. We continue in this fashion. The nth derivative, you see, let's look at the pattern. In the third derivative, the degree 3 term, the constant had been extracted with the 3 factorial in front of it. And all the variable from it was lost, right? So going by the same pattern, at this point it will be n factorial times am, and that's it. Right? This is the last term would have reached this thing when we do the nth derivative. Okay, so these are your derivatives. Now let's see how we can from here find the values of these coefficients, right? Again, let's try to keep a bigger picture clear there. We need to figure out these coefficients A0, A1, A2, A3, A4 based on the function we have. Okay? So I'm going to erase this. The derivatives I had earlier, if you plug in the value c into the x there, what happens? The function itself at c just becomes a0, right? Because it has all those other terms which are x minus c, x minus c, x minus c in them. Plug in c for x, you get c minus c, c minus c. All those become 0, only the constant term remains. Similarly, for the first derivative, if you plug in c, it will only be the coefficient of the linear term. For the second derivative, if you plug in c, you will get the coefficient. You will get 2a2. The third derivative, if you plug in c, you will get 3 factorial a3, and so on until you have the nth derivative. At c will be n factorial a n. Right? Okay. Now, these are the values of the function and its higher derivatives at c. These should equal the values of the function and its derivatives at c. Right? So this should equal f of c, where f is our original function that we are trying to approximate the polynomial. This should equal f prime of c. This should equal f second derivative of c. This will be the third derivative of c, and so on. This will be the nth derivative of c. Right? And from here, you see what happens. You can solve for the unknown coefficients, right? So a0 is f of c, a1 is f prime, a2 is second derivative of the function at c over 2, right? That's going to be 2 factorial to keep it consistent. Notation-wise, this from here you get a3 is the third derivative of f of c over 3 factorial, right? And so on. Here you get the nth coefficient is the nth derivative of f at c over n factorial. So now we are ready to define what is called, given the name, Taylor polynomial of a function at c. So keep in mind these coefficients, right?